What if I told you Earth's inner core isn't the solid sphere we've always thought it was? Scientists at USC have just discovered that 3,000 miles beneath our feet, the core is changing shape and shifting in real time. Imagine the ground beneath us pulsing like a living heart. This groundbreaking discovery, published in Nature Geoscience, forces us to rewrite textbooks. The boundary between our planet's solid inner core and molten outer core is undergoing a remarkable transformation that scientists are just beginning to understand. These deep Earth dynamics could potentially alter our planet's rotation and even affect the length of our days, a mystery with implications that stretch from the planet's depths to our daily experience. The crumbling shield above. The protective shield surrounding our planet is crumbling. Earth's magnetic field has been weakening at a rate of 5% per century, a concerning trend that's been documented for decades. What's truly alarming is that recent measurements indicate this rate isn't stable, it's accelerating. Scientists monitoring these changes have recorded weakening that's rapidly increasing beyond what natural decay should produce. This invisible field serves as Earth's primary defense system against the harsh environment of space. Without it, we would be constantly bombarded by deadly solar radiation and cosmic particles that would make life as we know it impossible. The magnetic field deflects these charged particles, creating a protective bubble around our planet that shields us from the sun's more dangerous emissions and cosmic rays originating from distant supernovas. The shield's weakening isn't uniform across the planet. Scientists have identified a massive weak spot called the South Atlantic Anomaly, a vast region stretching from Chile to Zimbabwe where the magnetic field is significantly weaker. This anomaly is actively growing and moving westward at approximately 12 miles per year, suggesting underlying instability in the field generating mechanisms deep within Earth. The International Space Station requires additional shielding when orbiting through this area, and satellites passing through regularly experience malfunctions as they're exposed to higher radiation levels that damage sensitive electronics. The historical record provides context for how unusual the current situation is. Scientists analyzing ancient pottery have made remarkable discoveries about our magnetic past. When clay is fired to create pottery, magnetic minerals within it align with Earth's magnetic field at that moment, preserving a record of the field's strength. Examining pottery from different historical periods, researchers have determined that field strength has decreased by approximately 20% in just the last 180 years, a rapid decline unprecedented in recent geological history. More precise measurements come from the European Space Agency's Swarm satellite constellation, launched specifically to study Earth's magnetic field. The magnetometer readings from these specialized satellites show the field's strength dropping most rapidly near the poles, where it's traditionally been strongest. The 3-satellite system has mapped these changes in extraordinary detail, revealing complex patterns that suggest fundamental changes in the field structure. The behavior of the magnetic field matches computer models that predict the early stages of a complete reversal or collapse. These models show that before a full reversal, the field typically weakens gradually, develops multiple poles rather than the normal 2, and exhibits growing anomalies like the one in the South Atlantic. The current observations align with these predicted patterns to a concerning degree. Like ice melting under intense heat, our magnetic shield is thinning and developing holes where protection fails. The connection between the magnetic field and Earth's core is direct and causal. The field itself is generated by the movement of molten iron in the outer core, a process called the Geodynamo. This massive electrical generator works because the liquid outer core flows and rotates around the solid inner core, creating electrical currents that produce our magnetic field. Any disruption to this system affects the field's strength and stability. When analyzing seismic data, which allows scientists to essentially see deep into the Earth, researchers noticed unusual vibrations at the core mantle boundary. These vibrations indicate turbulence and irregularities in the flow patterns of the outer core. The timing of these core disturbances correlates precisely with changes observed in the magnetic field strength. Scientists have detected that the field's increasingly erratic behavior stems from unprecedented movement at the core mantle boundary. This boundary, where the solid mantle meets the liquid outer core, is undergoing changes that weren't predicted by standard models of Earth's interior. Fluid dynamics at this boundary show patterns that suggest fundamental alterations in how energy transfers between the core and mantle. The European Space Agency's research team has published findings showing that molten iron in the outer core is moving in ways that weaken rather than strengthen the overall field. Normally, the complex flows of this superheated liquid metal amplify the magnetic field through the dynamo effect. The current flow patterns, however, include eddies and currents that work against the main field, contributing to its weakening. Advanced computer simulations comparing historical field behavior with current measurements show we've entered uncharted territory. Previous field weakening episodes in Earth's history typically occurred over thousands of years. The current rate of change is happening orders of magnitude faster, suggesting active disruption rather than natural variability. What makes these findings particularly concerning is that the magnetic field is becoming more chaotic. Stability has decreased alongside strength. The field's configuration is showing more variability than normal, with smaller local fields emerging and dissipating across different regions. This pattern of increasing chaos typically precedes major shifts in overall field structure. The implications extend beyond radiation protection. Earth's magnetic field influences everything from animal migration to atmospheric composition. Some species of birds, sea turtles, and bacteria use magnetic field lines for navigation. The changing field may already be disrupting these biological systems in ways we haven't fully documented. Weather patterns might also be affected. While the connection between the magnetic field and climate is still being researched, some studies suggest that field configuration influences the movement of charged particles in the upper atmosphere, potentially affecting atmospheric circulation patterns. In summary, our planet's magnetic shield is weakening at an alarming and accelerating rate. The rapidly growing South Atlantic anomaly, unprecedented core boundary movements, and satellite data all point to the same conclusion: fundamental changes are occurring within Earth's core that are compromising our protective magnetic shield. To understand why this shield is failing, we must journey deeper to the very heart of our planet, where the complex interactions between inner and outer core are undergoing significant changes that affect life on Earth's surface. Core revelations. What if the solid iron ball at Earth's core isn't actually solid at all? For generations, the textbook model of Earth's core has remained largely unchanged, a neat diagram showing a solid inner core surrounded by a liquid outer core. This fundamental understanding has shaped our perception of how our planet functions. But recent research published in Nature Geoscience by scientists at the University of Southern California suggests something that contradicts this basic premise. The inner core appears to be changing shape in real time. The implications of this discovery are profound. Since the 1930s, when Danish seismologist Inge Lehmann first proposed the existence of Earth's inner core based on seismic wave patterns, we've understood Earth's innermost layer as a solid sphere composed primarily of iron and nickel. This dense ball, roughly 1,500 miles in diameter, sits at temperatures comparable to the surface of the Sun and under pressures more than 3 million times that of Earth's surface. These extreme conditions force the iron atoms into a solid crystalline structure despite the intense heat. The liquid outer core surrounds this solid center, creating a layer of molten metal approximately 1,400 miles thick. This liquid layer flows around the inner core, generating Earth's magnetic field through its movement. The boundary between these two regions has been assumed to be relatively stable until now. The USC research team, led by seismologist John Vidal, discovered this phenomenon through innovative analysis of seismic data from 121 repeating earthquakes near Antarctica over 33 years between 1991 and 2024. These repeating earthquakes, occurring in the same location with nearly identical mechanisms, serve as perfect natural experiments for studying Earth's interior. Earthquakes generate different types of seismic waves that travel through Earth. P waves move through both solid and liquid materials, while S waves only travel through solids. By examining how these waves traveled through the inner core, the researchers found something unexpected. Instead of showing consistent timing and characteristics as expected with a solid core, the waves displayed subtle but significant variations over time that couldn't be explained by changes in the earthquakes themselves. Like a sculptor slowly remolding clay in real time, the core boundary appears to be undergoing viscous deformation. The team observed specific changes in wave travel times between the 1990s and 2020s. Waves arrived at different times and with altered characteristics, suggesting the boundary was physically reshaping itself. This deformation means the inner core isn't rigidly solid, but exists in a state between solid and liquid, a property called viscoelasticity. Materials with this property can resist sudden forces like a solid, but flow like a liquid when forces are applied over longer periods. What makes this discovery remarkable is that Vidal's team wasn't initially searching for evidence of a changing inner core. They were studying patterns of inner core rotation when evidence of core deformation emerged unexpectedly from their data analysis. The findings directly challenge our textbook understanding of Earth's structure. Rather than well-defined stable layers, we must consider a more complex reality where the boundary between solid and liquid at Earth's center is blurred and constantly changing. The traditional view that Earth's inner core solidified around 1 billion years ago and remains stable may need revision. The core might be more dynamic, with ongoing solidification and possible melting occurring simultaneously in different regions. This challenges fundamental assumptions about heat flow within Earth. The conventional understanding is that Earth is gradually cooling, with the inner core slowly growing as more of the outer core solidifies. The new findings suggest this process might involve regional variations and dynamic interactions between inner and outer core. The research team systematically ruled out alternative explanations like instrument drift or changes in earthquake characteristics. Technical analysis revealed that the deformation isn't uniform. Different regions change at different rates, suggesting complex flow patterns in the outer core affect the inner core boundary unevenly. The evidence points specifically to physical deformation rather than simple rotation. The seismic wave patterns showed characteristics consistent with the inner core surface being actively disrupted by the turbulent, flowing iron of the outer core on a timescale measurable over just decades, a blink of an eye in geological terms. This observation of relatively rapid changes deep within Earth forces us to reconsider our planet's internal workings. The most immediate question involves Earth's magnetic field, which depends critically on specific flow patterns in the outer core influenced by the inner core boundary. If that boundary is changing shape, it could alter flow patterns, potentially affecting the stability and strength of the magnetic field. This connection provides a possible explanation for the accelerating weakening of Earth's magnetic field that scientists have been observing. This discovery compels us to reevaluate everything we know about Earth's interior and how it generates the magnetic field that protects us. The complex relationship between the inner core's changing shape and the outer core's flow patterns might be the key to understanding why our magnetic shield is weakening and what that means for Earth's future. The magnetic engine. 3,000 miles beneath our feet, a massive engine constantly runs, converting motion into electricity on a planetary scale. This is the Geodynamo, Earth's magnetic field generator that creates the invisible shield protecting us from space radiation. Understanding how this engine works is critical to grasping what's happening as core changes accelerate. The Geodynamo operates through surprisingly straightforward physics, though at an enormous scale. Earth's outer core consists primarily of molten iron and nickel at temperatures exceeding 5,000 degrees Celsius. This superheated liquid metal surrounds the inner core and constantly moves due to convection currents created by heat escaping from the inner core. As Earth rotates, this moving metal generates electrical currents through electromagnetic induction, the same principle powering electrical generators in power plants. The process creates a self-sustaining system. When the conducting metal flows through an existing magnetic field, it generates an electric current, which creates its own magnetic field, strengthening the original field. The specific flow patterns in the outer core maintain this amplifying feedback loop. The solid inner core stabilizes these flows, creating the organized dipolar field with north and south magnetic poles that we rely on for protection and navigation. This delicate system requires a specific relationship between the solid inner core and liquid outer core. The boundary between these regions is crucial for proper field generation. The solid core provides stability while the flowing outer core supplies the necessary movement for electromagnetic induction. Significant changes to either component can destabilize the entire system. The USC study revealing inner core deformation directly impacts this balance. Changes in the boundary shape between inner and outer core alter the flow patterns that determine the magnetic field's strength and configuration. Even subtle alterations to these flows can significantly affect the field's overall structure. The rotation speed of the inner core presents another critical factor. Through seismic wave analysis, scientists discovered the inner core exhibits superrotation, spinning approximately 0.3 to 0.5 degrees per year faster than Earth's mantle and crust. Dr. Emma Richardson at the University of Leeds calls this the planetary equivalent of a wound-up spring, storing energy that helps drive our magnetic shield. This differential rotation creates shear forces at the inner-outer core boundary that organize flow patterns essential for maintaining our stable, strong magnetic field. Recent studies have detected something alarming. The inner core's rotation rate appears to have changed. Research published in Nature Geoscience analyzed decades of seismic data and found evidence suggesting the inner core's rotation has slowed significantly, possibly even reversing direction temporarily. Yi Yang and Xiaodong Song at Peking University compared nearly identical earthquakes from different decades to detect subtle changes in wave travel times through the inner core. Their analysis indicated the inner core's eastward rotation stopped around 2009 and may have reversed to westward rotation. This rotation change coincides precisely with the acceleration in magnetic field weakening measured by satellites, suggesting a direct causal relationship. Computer models demonstrate how disruptions to the inner-outer core boundary create turbulence in the geodynamo. When boundary shape or rotation patterns alter, the outer core flow becomes less organized, creating turbulent eddies that work against the main field rather than reinforcing it. These disturbances manifest as weakening magnetic protection in specific regions of Earth's surface, including the expanding South Atlantic anomaly. Earth's geological record confirms such changes aren't unprecedented. Deep-sea sediments contain iron-rich minerals that aligned with Earth's magnetic field when they settled on the ocean floor. By analyzing cores from these sediments, scientists have reconstructed a history of Earth's magnetic field stretching back millions of years, revealing dozens of complete reversals throughout our planet's history. The last complete reversal occurred approximately 780,000 years ago, with the average time between reversals being about 200,000 to 300,000 years. We're statistically overdue for another. Sediment cores also reveal shorter excursions where the field weakens dramatically without completely reversing, like the La Champe excursion about 41,000 years ago, when the field weakened to about 5% of its normal strength for approximately 1,000 years. What makes the current situation particularly concerning is the rate of change. European Space Agency satellites show Earth's magnetic field is weakening 10 times faster than natural decay would explain. Normal fluctuations typically occur at rates of 0.05%, 0.1% per year, while current measurements show rates approaching 0.5% to 1% annually in some regions. This acceleration matches models of active disruption rather than natural variability. Regional variations provide additional evidence of disruption. The South Atlantic anomaly is moving westward at approximately 12 miles per year, and satellite measurements have detected a second weak spot developing over the Pacific Ocean. Multiple simultaneous anomalies typically precede field reorganization according to historical data. If these core changes continue accelerating, we face a scenario that would fundamentally alter life on Earth's surface. The protection we've taken for granted, our invisible radiation shield, could weaken to the point of inadequacy. The geological record shows such weakening isn't just possible, it's inevitable on long enough timescales. The question isn't whether Earth's magnetic field will undergo significant changes, it's when these changes will occur and how rapidly they'll progress. Current data suggests we may have already entered the early stages of a major field transition, driven by unprecedented activity at Earth's core. The collapse timeline. Could our planet's magnetic shield vanish during our lifetime? For decades, geophysicists believed magnetic field reversals were slow, gradual processes that took thousands of years to complete. This timeline would theoretically give human civilization adequate time to develop technological adaptations and protective measures. The conventional understanding suggested that even if a reversal began tomorrow, our great-grandchildren, not us, would face the consequences of a significantly weakened field. But what if this reassuring timeline is wrong? What if magnetic field changes could occur within our lifetimes, transforming this from a distant geological curiosity to a potential near-term threat? Recent research presents compelling evidence for this. Accelerated timeline. The most striking evidence comes from ancient lava flows in Chile. When volcanic lava cools, magnetic minerals within it align with Earth's magnetic field, preserving a record of field direction and strength. Analysis of precisely dated lava flows revealed extraordinary field changes occurring approximately 16,000 years ago. The local field strength decreased at a rate of 6% per year. This rate is approximately 120 times faster than today's global weakening rate. These dramatic changes occurred over just a few decades, not millennia. Similar evidence exists in other regions. In Israel, researchers studying ancient pottery from the 8th century BCE discovered an extremely rapid spike in field intensity, approximately 50% increase in under 30 years before returning to normal levels. When scientists incorporate these historical rapid changes into models of current field behavior, the projections become concerning. Some models predict Earth's magnetic field could reach a critical weakening threshold within the next 100 to 150 years, the point where the organized dipole field becomes unstable and transitions to a chaotic configuration. Currently, the field is weakening at approximately 5% per century on average. However, this global average masks more dramatic regional changes. In parts of the South Atlantic anomaly, the field is already 30% weaker than expected and declining at an accelerating rate. If current trends continue, field strength in this region could decrease to less than 25% of normal values within 50 years. Advanced supercomputer simulations model the collapse sequence with remarkable detail. These models show the collapse would follow a specific pattern, beginning with expansion of existing weak spots like the South Atlantic anomaly. As the anomaly grows, it creates conditions that accelerate the weakening process through a feedback loop. The anomaly would spawn additional weak regions across the globe. Satellite measurements have already detected the formation of a second significant weak spot over the Pacific Ocean. These separate weak regions would eventually merge, creating large unprotected areas where cosmic radiation would reach Earth's surface with minimal deflection. As these weak spots expand, the organized dipole field would collapse into a multipolar configuration. Instead of two clearly defined magnetic poles, Earth would develop multiple, weaker magnetic poles scattered across its surface. This chaotic configuration provides significantly less protection against cosmic radiation and solar particles. The timeline for this transition varies by region. European Space Agency model projections suggest parts of South America and Africa would reach dangerously low field strengths first, potentially within 50 to 75 years if current acceleration continues. Europe and North America would follow, while Asia might maintain stronger field protection longer due to regional variations. During this transition period, which could last decades to centuries, different regions would experience varying levels of protection, creating significant challenges for global infrastructure, satellite operations, and radiation protection strategies. Most concerning is that current satellite measurements suggest this collapse process may have already begun. The International Geomagnetic Reference Field has documented accelerating change since 1990, with the 2020 update requiring larger than expected adjustments to account for rapid field changes exceeding previous projections. The South Atlantic anomaly has grown approximately 8% larger and 15% weak since the first satellite measurements in the 1970s, with growth accelerating in the past 2 decades. Simultaneously, the magnetic North Pole has increased its movement rate from about 10 kilometers per year in the 1990s to more than 50 kilometers per year, currently a five-fold acceleration unprecedented in historical records. When scientists compare these measurements with theoretical models of field collapse, the match is concerning. The pattern, rate, and regional distribution of weakening align with models showing early stages of either a full reversal or a major excursion, a temporary but significant weakening. The evidence converges on a worrying conclusion. Magnetic field reversals could occur much faster than previously thought, with significant weakening potentially happening within a century or less. This means people alive today might witness early stages of field collapse, with younger generations facing more severe consequences. However, even during previous reversals, the field typically weakened to approximately 10 to 20% of normal strength rather than disappearing entirely. This reduced field would still provide some protection, though significantly less than we currently enjoy. The accelerating weakening rate, growing anomalies, and inner core disruption match computer models of early-stage collapse with remarkable precision. These indicators suggest we may have entered the beginning phase of a magnetic excursion or full reversal, with changes occurring at rates relevant to human rather than geological timescales. The most sobering aspect is that we likely wouldn't recognize we had passed the point of no return until after it happened. By the time measurement networks detected unambiguous evidence of critical transition, the process would already be underway and potentially irreversible. But what exactly happens when our invisible shield fails? Radiation the consequences extend far beyond every day. Most people realize. Earth's surface receives a steady barrage of radiation from space. Our bodies evolved under the protection of an invisible shield that catches most of this harmful energy before it reaches us. This natural defense system, our planet's magnetic field, intercepts and redirects charged particles from the sun and distant cosmic sources, preventing them from striking Earth's surface at full force. The magnetic field deflects the constant stream of charged particles emanating from the sun known as the solar wind. These protons and electrons travel at nearly 1 million miles per hour when they reach Earth. Without this protection, these particles would strike our atmosphere directly, triggering cascades of secondary radiation that would reach the surface. The field also protects against galactic cosmic rays, high-energy particles originating from supernovas and other distant cosmic events. This protection is essential for life as we know it. Early Earth had no ozone layer, and life only moved from the oceans to land after the magnetic field and atmosphere provided adequate protection from harmful radiation. Our bodies simply aren't designed to handle extended exposure to space radiation, the very same invisible energy that silently damages cells and breaks apart the DNA that defines us. If Earth's magnetic shield weakens significantly or collapses during a reversal, radiation exposure at the surface would increase substantially. Models developed by NASA's Space Radiation Laboratory project that without our magnetic field, radiation levels would increase 3 to 5 times above current background levels across most of the planet. These estimates account for the atmosphere's continued protection, which would still block some radiation even without the magnetic field. Polar regions would face even higher exposure, potentially experiencing radiation levels up to 10 times normal. This geographic variation occurs because the weakened field would still deflect some particles toward the poles, concentrating exposure in these regions. The South Atlantic anomaly region, which already experiences higher radiation levels, would see these levels increase further as the field continues to weaken. Solar storms present particular danger during periods of magnetic field weakness. When the sun experiences coronal mass ejections, it sends billions of tons of charged particles toward Earth. During major solar storms, unshielded regions could receive radiation doses equivalent to multiple CT scans delivered over just 24 hours. For context, a single CT scan delivers about 7 millisieverts of radiation, while the annual background radiation dose averages around 3 millisieverts. Regions experiencing field collapse could see daily doses of 30 to 50 millisieverts during solar storms, enough to cause immediate radiation sickness with symptoms including nausea, vomiting, and immune system suppression. The biological impacts would be severe and widespread. Radiation damages living tissue by ionizing atoms, disrupting molecular bonds, and damaging DNA. Every 1,000 millisieverts of radiation exposure increases lifetime cancer risk by approximately 5%. If annual radiation exposure increased by just 10 millisieverts worldwide, due to magnetic field weakening, global cancer rates could increase by roughly 0.5% above current levels, resulting in millions of additional cancer cases globally. Radiation exposure also reduces fertility in both men and women, with male sperm production particularly sensitive to damage. Animal studies suggest fertility rates could decline by 20 to 40% in regions experiencing the highest radiation increases. Children face particular risk, as their rapidly dividing cells and developing organs are more susceptible to radiation damage, leading to developmental delays, cognitive impairments, and increased lifelong cancer risk. Plants and agriculture would suffer significantly. Controlled studies show decreased crop yields ranging from 15 to 30% depending on species and radiation intensity. Wildlife populations would experience increased mutation rates, reduced fertility, and shorter lifespans, as demonstrated in studies from radiation-affected areas like Chernobyl. The ozone layer would face additional stress, as high-energy particles accelerate ozone depletion. Models suggest depletion could increase by 3 to 7% globally during significant magnetic field weakening. This would allow more ultraviolet radiation to reach Earth's surface, creating a double exposure scenario where living organisms face both increased particle radiation from space and increased ultraviolet radiation from the sun. Certain areas, particularly those near growing magnetic anomalies, could become effectively uninhabitable during solar storms. Populations might become climate refugees, forced to relocate as radiation levels exceed safe thresholds. Countries lacking resources for radiation monitoring and protection would face greater impacts, potentially, triggering population movements from high exposure to low exposure regions. Infrastructure would also suffer. Satellites already experience malfunctions when passing through high radiation zones. As the magnetic field weakens, satellites throughout Earth orbit would experience increased exposure, shortening operational lifespans. Ground-based electrical grids would face increased risk of damage from geomagnetically induced currents during solar storms. The technology to monitor radiation exists, allowing early warning systems for acute exposure risks. However, the slow chronic increase in background radiation levels would affect populations gradually through increased cancer rates, fertility issues, and ecosystem impacts that would accumulate over generations. The danger isn't limited to invisible radiation. The core's disruption connects to more tangible threats emerging beneath our feet. The changing dynamics deep within Earth are potentially altering the stability of the ground itself. The connection between core processes and Earth's surface creates a complex web of interrelated hazards that compound one another. Tectonic triggers. While radiation from a weakened magnetic field presents a serious threat, another danger lurks beneath our feet. The seemingly solid ground we stand on is actually in constant motion. Earth's crust consists of massive tectonic plates that float atop the semi-liquid mantle, moving at rates of 2 to 5 centimeters annually. This perpetual movement builds tension along fault lines where plates meet, eventually releasing as earthquakes when the stress exceeds the rock's strength. For centuries, we've understood earthquakes as purely geological phenomena, the natural consequence of plate tectonics. However, recent research reveals a more complex reality. The frequency and intensity of seismic activity may be changing due to a combination of core dynamics and climate change. These connections suggest Earth systems are more interconnected than previously recognized. A groundbreaking study published in the journal Geology has identified a direct link between climate change and earthquake frequency. The research examined regions where large glaciers have recently melted, finding that the removal of ice weight allows underlying faults to move more freely. This process, called isostatic rebound, occurs as the crust rises after being relieved of the massive weight of ice that had compressed it downward for thousands of years. Evidence comes from the Sangre de Cristo Mountains in Colorado, where researchers documented fault slip rates increasing 5-fold following glacier retreat. By examining geological markers along fault lines, they determined that these faults had remained stable while compressed by glacial ice. Once the ice melted, the pressure release allowed the faults to slip more frequently, generating increased seismic activity. Similar patterns exist in Alaska, Greenland, and parts of Antarctica experiencing rapid ice melt. This relationship between melting ice and seismic activity creates a troubling feedback loop. Climate change accelerates glacial melt, which reduces pressure on underlying faults, which increases earthquake activity. The earthquakes can then damage permafrost and ice sheets, potentially accelerating melt rates further. Earth's crust essentially groans under these shifting weights, creating a climate tectonic feedback system that amplifies both climate impacts and geological hazards. The climate-seismic connection extends beyond melting ice. Scientists in northern Japan have discovered correlations between heavy precipitation events and earthquake swarms. Research published in Science Advances analyzed precipitation data alongside seismic records, finding that intense rainfall often preceded unusual clusters of small earthquakes by several days to weeks. Water penetrates deep into fault systems, reducing friction between rock surfaces and altering subsurface pressure. When water infiltrates fault zones, it lubricates the fault and reduces the force needed to trigger movement. This hydroseismic triggering has been observed in multiple regions worldwide where unusual precipitation patterns have occurred. These climate-triggered earthquakes have become increasingly common during precisely the same period that core changes have accelerated. The timing suggests these phenomena may be interconnected through complex Earth systems that we're only beginning to understand. The correlation highlights how multiple Earth systems can experience simultaneous perturbations that compound each other's effects. Perhaps most concerning is the emerging evidence connecting core dynamics directly to surface seismic activity. Earth's core influences our planet's rotation through complex fluid dynamics. As molten material flows within the outer core, it creates subtle shifts in mass distribution that can slightly alter Earth's rotational behavior. These changes are extremely small, measured in milliseconds of day length, but they redistribute enormous energy through the planetary system. Research from Caltech's Seismological Laboratory has identified correlations between changes in Earth's rotation rate and periods of increased global seismic activity. By analyzing decades of rotational and seismic data, researchers found that slight rotational slowing often preceded years with above-average numbers of significant earthquakes worldwide. The mechanism relates to angular momentum conservation. When Earth's rotation slows slightly, the reduced centrifugal force changes stress patterns throughout the crust. These stress changes concentrate along existing fault lines and plate boundaries. The additional stress can push already strained fault systems past their breaking points, triggering earthquakes in vulnerable regions. Core disruptions amplify these effects by adding variability to Earth's rotation. The USC study showing changes at the inner-outer core boundaries suggests that flow patterns generating Earth's magnetic field are becoming more chaotic. These changing flow patterns affect mass distribution within the core, potentially creating more variable rotational effects that translate to irregular stress patterns in the crust. Evidence for these connections comes from multiple independent sources. Satellite measurements tracking variations in Earth's rotation show increasing irregularity over the past 2 decades. Simultaneously, global earthquake catalogs reveal measurable increases in both the frequency and clustering patterns of significant seismic events worldwide. The correlation between these datasets is statistically significant according to analyses published in Earth and Planetary science letters. We're seeing evidence of unusual seismic patterns. The New Madrid seismic zone in the central United States has shown increased activity despite being far from any plate boundary. Intraplate earthquake swarms in Oklahoma, Texas, and Ohio have increased dramatically in recent years. While some activity relates to industrial fluid injection, the broader pattern suggests fundamental changes in crustal stress distributions that align with predictions from core rotation models. The combination of climate-driven and core-influenced seismic triggers creates compounding risk. Regions experiencing glacial melt face increased earthquake probability from isostatic rebound. Areas with changing precipitation patterns face additional risk from hydroseismic triggering. Globally, shifting stress patterns from rotational irregularities add another layer of seismic potential. These mechanisms can operate simultaneously in vulnerable regions, potentially triggering earthquakes that might otherwise have remained dormant for centuries. This complex interplay between Earth's systems makes earthquake prediction increasingly difficult. Traditional seismic forecasting relies on historical patterns that may no longer apply in our changing world. Disaster preparedness must now account for these new triggers, especially in regions facing multiple risk factors simultaneously. As Earth's systems become more interconnected and unstable, our ability to anticipate when and where the next major earthquake might strike becomes more challenging, demanding new approaches to both science and public safety. Volcanic chain reactions. We once thought volcanic systems operated in isolation, with each volcano functioning as its own independent entity. This comforting assumption has been thoroughly disproven by recent research. Volcanologists have discovered extensive interconnected magma networks that can span hundreds of miles beneath the surface, potentially linking volcanic systems across continental boundaries. These findings reveal Earth's volcanic infrastructure as vastly more complex and interconnected than previously understood. The connections between volcanic systems exist through the mantle, the semi-fluid layer between Earth's crust and core. Using seismic tomography, which creates three-dimensional images of Earth's interior by measuring how seismic waves travel through different materials, scientists have mapped extensive magma highways beneath volcanic regions. These pathways allow pressure changes in one area to potentially influence volcanic behavior in distant systems. Changes in core dynamics could potentially activate these volcanic networks through their effects on mantle convection patterns. The mantle flows in massive convection cells that transfer heat from the core to the crust, determining where magma rises toward the surface and influencing volcanic activity worldwide. The inner core boundary dynamics revealed by the USC study could significantly alter these convection patterns. As the boundary between inner and outer core undergoes viscous deformation, it changes how heat transfers from the core to the mantle. These thermal changes can create pressure variations that propagate through the mantle, potentially reaching volcanic systems thousands of miles away. This interconnected system behaves like an elaborate network of dominoes. When one falls, it can trigger a chain reaction affecting the entire arrangement. Laboratory experiments at ETH Zurich's Department of Earth Sciences demonstrate why this occurs. Using specialized chambers that simulate conditions deep within Earth, researchers found that pressure changes as small as 1 to 2 bars, equivalent to about 2% of atmospheric pressure at sea level, can initiate magma movement in previously stable systems. A minor pressure increase in one magma chamber can push magma into connected chambers, increasing pressure there and potentially triggering movement in systems that were previously stable. This creates the potential for chain reactions across vast distances, with catastrophic implications for regions that might otherwise consider themselves safe from volcanic threats. Historical records provide compelling evidence that periods of magnetic field instability often coincide with increased volcanic activity. By examining ice cores and deep-sea sediments, scientists can identify both volcanic ash layers and evidence of magnetic field changes preserved in the same chronological sequences. The leaf champ excursion from approximately 41,000 years ago offers a dramatic example. During this brief period, Earth's magnetic field temporarily reversed and weakened to about 25% of its normal strength. Ice core records show volcanic sulfate deposits increased by approximately 300% compared to background levels. Ash fingerprinting techniques indicate eruptions occurred nearly simultaneously across volcanic systems in Iceland, the Mediterranean, and the Pacific Ring of Fire, precisely when the magnetic field reached its weakest point. Another striking case occurred approximately 780,000 years ago during the Brunn-Mathieu reversal, when Earth's magnetic field completely flipped polarity. Geological records show a 200 to 250% increase in volcanic activity globally compared to normal background rates, spanning multiple tectonic settings. Modern monitoring systems are detecting unusual magma movement patterns that correlate with the timing of observed core disruptions. The Global Volcanism Program has documented increasing unrest across multiple volcanic systems since approximately 2010, coinciding with the period when inner core rotation changes were first observed. Particularly concerning are simultaneous inflation patterns at volcanoes in Alaska, Iceland, and Chile that began within months of each other despite being separated by thousands of miles. Satellite radar interferometry has measured similar uplift patterns at these distant sites, suggesting a common triggering mechanism. The Yellowstone supervolcano caldera has shown unusual inflation and seismic patterns that began accelerating around 2014, coinciding with the period when magnetic field weakening rates increased. The pattern of seismic activity has shifted with earthquake swarms occurring in new locations that hadn't previously experienced significant activity. If these connections between core dynamics and volcanic activity prove causal rather than coincidental, the implications are profound. We could potentially see synchronized eruptions across volcanic systems previously thought to be independent, creating compound disasters far beyond what emergency management systems are designed to handle. During previous excursions and reversals, volcanic activity increased globally by 200 to 300%, with eruptions often clustered in time despite occurring in geographically distant locations. If similar patterns develop today, multiple large eruptions occurring within a short time frame would inject unprecedented quantities of sulfate aerosols into the stratosphere, potentially causing global cooling of 1 to 2 degrees Celsius for several years. This cooling would disrupt agricultural systems already stressed by climate change. Aviation would face particular challenges from multiple simultaneous eruption plumes. During the 2010 geological eruption in Iceland, European air traffic was severely disrupted for weeks by a single moderate eruption. Multiple simultaneous eruptions across different regions could potentially ground global air traffic for extended periods. Increased stratospheric aerosols would accelerate ozone depletion, potentially worsening radiation exposure issues already expected from magnetic field weakening. This would create a compounding situation where both ground-level radiation and UV exposure increase simultaneously. Volcanic hazards combined with magnetic field weakening create a troubling scenario where multiple Earth systems fail simultaneously rather than in isolation. The historical record suggests these combined events have occurred previously during periods of magnetic field instability, though past occurrences happened when human population was minimal and before complex global infrastructure existed. These geological threats would be devastating on their own, but they're compounded by another consequence of our changing planet: rising seas, rising waters, shifting ground. The coastal edges of our continents face a twofold threat that few researchers have examined in combination. Rising seas are meeting increasingly unstable ground, creating compound hazards that neither climate scientists nor geologists fully anticipated. This intersection represents a new frontier in Earth system science, one where oceanic changes interact with geological instability in potentially catastrophic ways. Sea levels have risen approximately 8 to 9 inches since 1880, accelerating in recent decades due to thermal expansion and melting ice sheets. The IPCC projects an additional rise of 2 to 7 feet by 2100, forming the basis for coastal adaptation plans worldwide. Yet, geological evidence suggests these projections may underestimate the threat. During the last interglacial period about 125,000 years ago, when temperatures were only 1 to 2 degrees Celsius warmer than pre-industrial levels, sea levels were approximately 18 feet higher than today. This finding becomes alarming when we consider the time frame. This transition occurred within centuries rather than millennia, indicating feedback mechanisms in ice sheets that accelerate melting when certain thresholds are crossed. Like water pressing down on a fragile foundation, rising seas place additional weight on coastal margins, stressing already vulnerable fault systems. The relationship works both ways. Geological activity affects sea levels, and changing sea levels trigger geological events. As water depth increases, the additional weight creates vertical stress that translates into horizontal forces along angled fault planes. Even small stress changes can trigger movement in faults near their breaking point, particularly in regions with relatively thin crust-like continental margins where major population centers have developed. Imagine coastal residents facing dual threats: the slow encroachment of rising waters gradually claiming homes and businesses, while simultaneously feeling the sudden jolt of earthquakes where none were expected. This isn't a distant scenario. It's already beginning to unfold in vulnerable coastlines around the world. Research published in Geophysical Research Letters has documented increased microseismic activity along the eastern seaboard of North America, correlating with sea level changes, despite this region lying far from active plate boundaries. Similar patterns have emerged along coastlines in Japan, New Zealand, and the Mediterranean, with moderate earthquakes occurring in historically stable regions during periods of accelerated local sea level rise. The implications for infrastructure are profound. Approximately 40% of nuclear power plants worldwide are located in coastal zones, designed according to historical sea level and seismic assessments now rendered obsolete. Chemical plants, ports, and transportation hubs concentrate along these same vulnerable coastlines, creating potential for cascading industrial accidents triggered by combined sea level and seismic events. Beyond direct earthquake triggering, rising seas create secondary geological hazards. Coastal erosion accelerates as waters advance, destabilizing slopes and increasing landslide risk. Saltwater intrusion changes subsurface pressure regimes, affecting ground stability. Increased groundwater pressure reduces soil cohesion, potentially liquefying sediments during seismic events, a process responsible for extensive damage during earthquakes in Christchurch and Mexico City. This creates a dangerous feedback loop. Coastal earthquakes can trigger submarine landslides, potentially releasing methane hydrates stored in continental shelf sediments. These vast methane reserves, once released, accelerate climate change, increasing ice melt and sea level rise, which further destabilizes coastal fault systems. The redistribution of weight from melting ice and rising seas affects Earth's rotation rate. While these rotational changes measure only milliseconds, they redistribute enormous forces throughout Earth's systems. Research from NASA's Jet Propulsion Laboratory indicates these variations can affect mantle flow patterns and potentially core dynamics. In polar regions, melting ice sheets allow the crust underneath to rise through isostatic rebound, changing stress patterns across entire regions and potentially triggering earthquakes along distant faults. GPS measurements in Greenland and Antarctica show crustal uplift occurring faster than predicted, indicating rapid changes in subsurface stress patterns. The combination creates potential for compound disasters, earthquakes triggering tsunamis that impact already flooded coastal regions, overwhelming emergency response systems designed for isolated events. Communities already adapting to flooding suddenly face seismic threats, with evacuation routes compromised by elevated waters. Traditional disaster response models address hazards individually, flooding separately from earthquakes or tsunamis. The prospect of simultaneous events challenges fundamental assumptions in emergency management. Resources deployed for flooding become unavailable for earthquake response, while evacuation routes designed for tsunami escape may be compromised by previously elevated sea levels. Academic disciplines have traditionally remained separate, with climatologists studying sea level rise, while seismologists study earthquakes. This separation has prevented full appreciation of these interacting systems. Emerging interdisciplinary research is beginning to bridge these gaps, creating comprehensive models incorporating both oceanic and geological processes. The evidence suggests we must prepare for compound disasters rather than isolated events. Rising seas meeting increasingly unstable ground creates risks exceeding the sum of their parts. Successfully addressing these interconnected hazards requires similar interconnection between scientific disciplines, policy approaches, and emergency response systems. With these threats converging, weakening magnetic fields, accelerating core dynamics, increasing seismic activity, volcanic interconnections, and rising seas, humanity must develop both technological monitoring systems and potential intervention strategies to track and perhaps mitigate some consequences of our increasingly unstable planet. As Earth's core undergoes unprecedented changes, scientists have deployed an array of sophisticated monitoring systems to track these transformations in real time. Unlike previous geological eras when core changes went unobserved, we now possess technology capable of detecting subtle shifts in our planet's deepest regions. These monitoring networks represent humanity's early warning system for potential core collapse. The European Space Agency's Swarm mission stands at the forefront of this monitoring effort, Launched in 2013, this constellation of 3 identical satellites orbits in precise polar paths between 450 and 530 kilometers above Earth. Each satellite carries extraordinarily sensitive magnetometers that detect magnetic fields changes as small as 1 nanotesla, approximately 1/50,000th of Earth's average field strength. Their strategic orbital configuration allows scientists to separate core-generated magnetic signals from those produced by the crust, ionosphere, or solar activity. Swarm's data quickly revealed concerning developments. The satellites detected magnetic field weakening occurring significantly faster than previous measurements had indicated, particularly in the South Atlantic region, where field strength was decreasing at rates up to 10 times faster than global averages. More concerning was the discovery of a second significant weak spot developing over the southern Indian Ocean. The emergence of multiple simultaneous anomalies matches theoretical models of early-stage field collapse. On the ground, the International Real-Time Magnetic Observatory Network, Intermagnet, complements these space observations. This network of over 130 observatories spans all continents, continuously measuring field strength and orientation. Beginning around 2014, stations across multiple continents recorded rapid directional shifts in local magnetic field orientation, occurring over months rather than the expected decades. These shifts follow mathematical patterns consistent with early-stage field collapse. While magnetic monitoring tracks the symptoms, seismic networks allow scientists to observe the core's condition directly. The International Monitoring System includes 170 seismic stations worldwide that record Earth's internal vibrations. By analyzing how seismic waves travel through Earth's interior, researchers can create images of deep structures. Recent observations show expanding areas of ultra-low velocity zones at the core mantle boundary, regions where seismic waves travel abnormally slowly. These zones appear to be growing beneath the South Atlantic and Pacific regions, correlating geographically with the observed magnetic anomalies. Earth's rotational behavior provides additional evidence of core changes. The International Earth Rotation and Reference System Service measures Earth's rotation with microsecond precision using laser-ranging satellites, radio telescopes, and GPS receivers. These measurements show increasing irregularity in rotation rate and pole position over the past 2 decades. The variations exceed predicted ranges and correlate temporally with observed magnetic and seismic changes, suggesting disruptions in the outer core's flow patterns. This global symphony of data, magnetic, seismic, gravitational, and rotational, creates a comprehensive picture of Earth's interior dynamics. The volume and complexity of information from these monitoring networks have necessitated the development of advanced artificial intelligence systems designed to identify patterns in multidimensional geophysical data. Machine learning algorithms continuously analyze incoming data, searching for indications of critical transitions before they become obvious to human observers. A research consortium, including MIT, the Max Planck Institute, and Beijing's Institute of Geology and Geophysics, has developed neural networks specifically optimized for detecting precursor signals of rapid field changes. These systems have identified subtle correlations between field configurations and subsequent weakening that traditional analysis missed. Recently, AI monitoring flagged concerning patterns in North Atlantic field dynamics, increasing high-frequency oscillations superimposed on the general weakening trend, similar to patterns that preceded rapid field changes in computer simulations of previous reversal events. Despite these advanced capabilities, scientists remain divided on interpreting the data. Some view the observations as evidence of accelerated but normal variations, while others see clear signals of a field entering early-stage collapse that could progress to a full reversal within centuries or potentially decades. This uncertainty stems partly from limitations in our understanding of core processes. Even with current technology, we observe the core indirectly through its effects rather than directly imaging its structure. The International Association of Geomagnetism and Astronomy has established a core collapse assessment group to evaluate monitoring data and refine prediction models. Their latest assessment acknowledges that current observations fall outside the range of historical field behavior recorded over the past 400 years of direct measurement. This integrated global monitoring network provides unprecedented insight into core behavior, allowing researchers to track changes as they happen and potentially forecast critical transitions. Yet monitoring represents only the first step in addressing potential core collapse. These systems can tell us what's happening, but not necessarily how to respond. Scientists face a sobering reality. Observation might be our only option. Unlike climate change or other human-influenced Earth systems, core dynamics operate at scales and depths that may remain beyond our technological reach, regardless of how clearly we can track their evolution. The question remains whether humanity possesses the knowledge and technology to influence deep Earth processes if monitoring indicates acceleration toward critical thresholds. But monitoring isn't enough. What can humanity actually do if the core collapse accelerates? Surviving the unthinkable. Throughout human history, we've faced natural disasters, pandemics, and wars, but never a threat that originates 3,000 miles beneath our feet and affects the entire planet simultaneously. The potential collapse of Earth's magnetic field presents precisely this kind of unprecedented challenge. Unlike localized disasters where unaffected regions can provide aid, a core-driven catastrophe would impact the entire globe, though with varying intensity across different regions. While we cannot prevent changes in Earth's core or reverse the weakening of the magnetic field, scientists and engineers have begun developing technologies and strategies to mitigate consequences. These approaches range from adaptations of existing technologies to theoretical planetary scale interventions. Creating artificial mini-magnetospheres around critical infrastructure builds on technology already used in experimental fusion reactors. Powerful superconducting magnets could generate protective bubbles that deflect charged particles around specific areas. The European Organization for Nuclear Research has conducted studies suggesting magnet arrays could provide meaningful protection over areas several kilometers in diameter. These systems would require enormous energy and specialized materials. However, they could protect power plants, water facilities, and hospitals during periods of field weakness. Consider how a city like Tokyo, where researchers are testing early prototypes, might deploy these shields around its power grid, potentially saving millions from extended blackouts during a major solar event. Underground facilities offer more immediate protection during radiation events. Earth itself provides excellent shielding, with a few meters of soil blocking most cosmic radiation. Existing subway systems and bunkers could become temporary radiation shelters with modifications to air filtration and communication systems. Switzerland's model demonstrates practical implementation. Their civil defense includes shelters sufficient for the entire population. Unlike nuclear bunkers designed for months of occupation, cosmic radiation shelters would only need to house people during peak radiation periods lasting hours to days. Imagine a community in Zurich taking shelter in converted facilities as warning systems announce an incoming solar storm, emerging safely after the danger passes. Electronic systems present particular vulnerability. The radiation-hardened electronics used in satellites employ specialized materials and design techniques, redundant circuits, error-correcting memory, silicon-on-insulator technology, and specialized shielding. While currently expensive, these technologies could be implemented in critical infrastructure to maintain basic functionality during radiation events. Agricultural production faces dual challenges: direct radiation damage to crops and disruption of pollinator navigation. Research institutes have already identified rice varieties with higher radiation tolerance than common strains. Similar work with wheat, corn, and soybeans has found genetic markers for radiation resistance. Indoor and underground farming systems provide another layer of agricultural resilience by shielding plants from external radiation. More ambitious approaches include deploying a solar shield at the Lagrange point L1, a stable position between Earth and Sun. This shield would block incoming solar particles before they reach Earth. Preliminary designs suggest multiple smaller units rather than a single structure. The European Space Agency studies indicate a shield covering just 2 to 4% of Earth's cross-sectional area could provide significant protection during solar events. Even more theoretical proposals involve attempts to influence core. Dynamics through technologies that don't currently exist, from vibration arrays altering flow patterns in the outer core to directed energy approaches stimulating favorable convection patterns. These represent aspirational technology rather than near-term solutions. Practical preparation requires a multi-layered approach, early warning systems using satellite networks to monitor dangerous solar events, giving hours to days of notice before radiation reaches dangerous levels. Hardened infrastructure maintaining essential services, including robust power grids with distributed generation, protected water treatment facilities, and resilient food production. Strategic retreat from high-risk regions near magnetic poles and within growing field anomalies like the South Atlantic anomaly. Knowledge preservation, ensuring information about magnetic field dynamics is widely distributed rather than concentrated in specialized scientific communities. The human dimension remains crucial. Consider a farmer in Nebraska whose family has worked the same land for generations, now experimenting with radiation-resistant crop varieties. Or emergency managers in Sao Paulo, coordinating evacuation drills as the South Atlantic anomaly grows. These individual and community-level adaptations, multiplied across societies, represent our most realistic defense. As we face this threat, we confront a fundamental question about Earth's future. How will human civilization respond to a changing planet that challenges our assumptions about environmental stability? While complete protection exceeds our current capabilities, strategic adaptation could significantly reduce impacts on human society. The coming decades will test whether our scientific understanding can translate into practical measures that preserve civilization through one of the most profound planetary transitions humans have ever faced. Earth's core isn't the unchanging sphere we imagined. What we're discovering forces us to see our planet not as a stable platform, but as an active, evolving system in constant flux. The evidence points to transformations occurring far faster than geological timescales suggested possible. While we can't prevent these deep planetary changes, we can prepare with monitoring networks, protective technologies, and adaptation strategies. Our response to this emerging reality will determine our future. Can we, as a civilization, rise to meet a planet that is rewriting its own destiny? Earth will change. Our survival depends on whether we can adapt quickly enough on this increasingly dynamic world.